Okay, great. Let's get started. So today I'll be going over how to design a language agnostic SDK for cross-platform deployment and maximum extensibility. So just before we start, here's just a bit about me. I'm one of the core C++ developers at TrueFace, which is the sponsor for this event. I'm heavily involved in building our C++ SDK, and I'm currently leading our embedded thermal solution, which automates the temperature detection process. And I think it's pretty cool. You can see it in the bottom right of the screen. I use a lot of the techniques which I'll be discussing in this presentation today, both at TrueFace and in my personal projects. So what can you expect to learn today? From what I personally found, tutorials online only cover a single topic and really dive into that. Unlike that, today we'll cover the entire start to finish process of SDK design. So it should really be enough to get you started on your next big project. I'll be focusing less on the actual code architecture and best practices, because if you want to learn about that, you're probably better off listening to some CPP Con talk. Instead, I'll be focusing on the things outlined on this slide. So that includes how to build a basic computer vision library in C++, how to compile and cross-compile that library for AMD64, ARM64, and ARM32, how to package that library and its dependencies all as a single static library, how to add unit tests for that library, how to set up a continuous integration pipeline, how to write Python bindings, and finally, how to generate documentation directly from our API. Some of the tools I'll be going over today include Linux, C++, CMake, GCC, Catch2, OpenCV, PyBind 11, CircleCI, NCNN, and Doxygen. Finally, if you want to follow along with the completed code, there's a link to the GitHub repository. I've also put it in the chat, so you're welcome to follow along there. Just to touch on the structure of this presentation, this is not going to just be a high-level overview. I'll actually show you how it's done in the code itself. Though do realize that sometimes I can't fit all the code onto the screen, so I've selected small snippets of the code to show. Okay, so what are we going to build today? Today we're going to build a face and landmark detection SDK. The ability to detect faces is quite useful because it is the first part of many pipelines, including face recognition, face blurring, amongst other things. So both those GIFs you saw in the second slide there, they both started with face detection as being the first step. So for today's tutorial, I'll be working on Ubuntu. I'll be assuming you have a little bit of knowledge in how to use your terminal, C++, maybe even a bit of CMake knowledge. But if you're totally unfamiliar with these things, don't worry. You can still follow along and learn a thing or two. Okay, so why do we want to use C++ for our SDK? Performance is the primary reason. So it's no secret that C++ is a very fast programming language. It's low level enough to give us the speed we desire, while having minimal added runtime overhead. In computer vision, we generally manipulate lots of we manipulate lots of images, which can contain huge amounts of data. We perform matrix operations, we modify color spaces. Therefore, performance really is critical. For example, if we have a real-time application and we want to achieve a certain frame rate to make it look good, then our app sure as hell better be fast in order to reduce the latency. Some other advantages, if we compile our code for a certain architecture with C++, then we can run it there without needing any interpreters on that device or anything like that, just as long as the dependency libraries are present, such as libstd C++, libc. Also, it's easy to distribute. So I'll be going into that more later in the presentation. So what is the structure of our project going to look like? So this is kind of what the hierarchy of our project is going to look like in terms of the directories. So I'll just go over what each of these is going to be. So the third-party directory is going to contain our third-party dependency libraries, and I'll go over what these are going to be later. The dist directory is going to contain the distributables generated by our SDK. So this is going to be the include header file and also the static library itself. Docker is going to contain the Docker files required for our CircleCI pipeline. Docs is going to contain the build scripts for generating the documentation. Include is going to contain any include headers that we want to ultimately distribute to the end user. Models is going to contain the machine learning models, which are used for inference. Python is going to contain the scripts and source code used to generate the Python bindings. The source directory is going to contain any of our C++ source files, but in addition to that, it'll actually include our other header files, which we don't want to distribute to the end user. So these are kind of like the internal header files. The test directory is going to contain our unit tests. And finally, the tools directory is going to contain our toolchain files. And one of them that is not shown here, because it's a hidden directory, is called the .circle-ci directory. And that's going to be used for our CI pipeline. So the first thing we're going to need to do is install our third-party dependencies. And the third-party dependencies we require for this project are going to be NCNN, which is a lightweight machine learning inference library, which is optimized for CPU and in particular mobile devices. We're going to be using OpenCV, which is a very popular open source computer vision library used for kind of image manipulation, but it honestly does a ton of stuff. We're going to be using Catch2, which is a unit testing framework, and finally PyBind 11, which is a Python bindings framework. So the latter two libraries are header only, meaning we only require the source files, whereas the first two libraries, NCNN and OpenCV, they actually need to be compiled. So there's a few ways to include these in our project. We can add them as Git submodules and use CMake to compile the libraries when we compile our own library. I'm personally not a fan of that. I prefer using shell scripts, which can be used to grab the source code, extract it, and then compile it for all the desired platforms, which in our case is AMD 64, ARM64, and ARM32. So just to touch on what's on the slide here, this is kind of like a sample snippet from one of the build scripts. This is for building NCNN, and kind of the most important part you'll see is that we basically create a build directory. We call CMake with all our arguments, and then we build the code using make. And kind of what I want to point out here is the main difference between the AMD 64 version, which is kind of your typical x86 architecture, and the ARM32 version is in the ARM32 version, in addition to like a few extra flags we have to add just to tweak things, we also have to pass this CMake flag called CMake toolchain file. And basically what that is it's telling CMake what cross compiler it should use in order to compile that library. So later in the presentation, I'll be touching more on what a cross compiling toolchain looks like. But just for now, I want you to just see what kind of like one of the install scripts looks like, pardon me. So we have a similar build script for OpenCV. We can go ahead and run these, and now we should have all our dependency libraries installed. So now we're going to talk about our actual library. Since I'm a very creative person, I decided to name my library my SDK. So this is what our API looks like. We have a few structs in our namespace. We have a single enum. And then we have one public-facing member function called getFacebox and landmarks. So our class API function is basically going to take an image path, and then it's going to take two other variables by reference, a Boolean, and then this struct, a vector of this struct, which we've defined up here. And it's basically going to detect all the faces in that image and then return a list of the facebox and landmarks. So I'm actually not going to show what the implementation of our API function looks like just for the sake of time. If you're interested, you can look at the code on GitHub repository. It's all there. But basically, we perform machine learning inference using some open source models to detect all the faces. What I do want you to notice, though, is the design pattern that we are using here. So what you'll see in the private section of this class right here is that we're using this p-impl. And what that is that we're hiding the private members from the end user through the use of a pointer to an implementation class, which we have forward declared. So this implementation class is kind of where we have all our logic and our additional class member variables and class member functions. And in doing this, not only do we hide the private member variables and therefore the implementation from the end user, but it also allows us to include only the bare minimum number of headers we require. So for example, I can already tell you that the implementation class is going to use a member variable, which is going to be an instance of the NCNN inference engine class. So if we were to define that member variable here in our API header, then we would have to either forward declare that NCNN class, or we'd have to actually include the NCNN header, which is a big no-no, because that means the end user would have to have NCNN actually installed on their machine in order to compile against our library. Okay. So I know I said I wasn't going to go over the details of the implementation, but there's something that I think is worth mentioning. By default, the open source face detector we're using, called MTCNN, loads the machine learning models files at runtime. Now, this isn't ideal because it means we'll have to distribute these machine learning models with our SDK, and it just means it's something extra that we have to ship to the user. And the whole point is that we're trying to reduce the number of things that we provide to the user. So we can therefore use this somewhat of a hack, I guess, to convert the model files to header files. So the xdd bash command is basically a command used for generating hex dumps. We can then include the models in our code like normal header files and load them directly from memory. Therefore, if we do this, the model files actually become embedded into our SDK, and we don't need to distribute them separately. Just note though that with large model files, converting to header files takes up way too much memory and just isn't practical. So you'll probably want to convert it directly to an object file, which I won't be going over in this tutorial, but you can look that up online on how to do that. So we can now use CMake to generate the build files for our project. So in case I didn't mention it already, CMake is a build system generator used to manage the build process. This is what part of the root CMake list.txt look like. Unfortunately, the tool I'm using to generate code snippets doesn't have syntax highlighting for CMake, so you'll just have to bear with me for the next few slides. But basically, we're creating a static library called my SDK static, which you can see right here. And it's going to contain our implementation. So we're compiling our two source files, my_sdk.cpp and mtcnn.cpp. The reason we're creating a static library is because in my experience, it's easier to distribute it to users. If we were to build a dynamic library, we'd have to worry about dependency versions. We might even need a manifest associated with our libraries. Whereas with a static library, we can literally just send the client the static library and the header, and that's it. They can just compile their program against our library. Statically linked libraries also do have a slightly better performance profile than dynamic libraries, but that's pretty minor. So basically next, we tell CMake where to find the necessary include header files so that our source files, we tell CMake where to find the necessary include header files that our source files require, pardon me. Something to note though, although this will build our library right now as is, when we try and link against our library, we'll find that we'll get an absolute ton of undefined reference to symbol errors from both OpenCV functions and NCNN functions. So if we were to link against our static library at this point in an executable, for example, we'd also need to link all the dependency libraries too. Unlike dynamic libraries, static libraries can't resolve their own dependencies. They're basically just a collection of object files packaged into an archive. So later in this presentation, I'll demonstrate how we can bundle all the dependencies libraries with our own library so that the user doesn't need to worry about tracking down or linking any of these dependency libraries. So many computer vision applications are deployed at the edge. This includes the use of embedded devices, which generally have ARM CPUs. We must therefore compile our library to support these architectures if we want to support deploying at the edge. Just to touch on the difference between ARM32 and ARM64, also called Arch32 and Arch64, is that Arch64 refers to the 64-bit extension of the ARM architecture. So for example, even though the Raspberry Pi 4 has a 64-bit ARM CPU, the default operating system Raspbian is 32-bit, therefore it would require an Arch32 compatible binary. Whereas if we choose to run a 64-bit operating system on the Raspberry Pi 4, such as Gen 2, then it would require a Arch64 compiled binary. So another example of an embedded device, is the NVIDIA Jetson, which has an onboard GPU and runs Arch64. So in order to cross-compile, we need to tell CMake that we are not compiling for the architecture of the machine we're currently using, but that we want to compile for a different architecture. This is kind of done through the use of different toolchains. And what a toolchain does kind of what a toolchain file does, pardon me, is that it's used to specify which compiler CMake should use. So for example, for Arch64, which is shown on the left here, we would use the Arch64 Linux GNU G++ compiler, whereas for Arch32, which is shown on the right here, we need to use the ARM Linux GNU-BIF G++ compiler. Quite a mouthful, I know. And the HF in GNU-BIF stands for hard float. There's a bit more to these toolchain files, which I haven't shown here, but I think selecting the compiler, which is shown in these slides, is definitely the most important part, which I want you guys to definitely understand. So right at the top of our root CMake list.txt, we can then add the following lines of code. Basically, we're adding CMake options, which can be enabled in order to cross-compile. So here you'll see that we've added two options, build ARM32, build ARM64, and these options can be set in the command line when we're building our library. So you would add a -d build underscore ARM32 equals on if you wanted to enable this option, for example. So what will happen then is that if the person selects this option and enables it to true, then we select the appropriate toolchain file and tell CMake to use a cross compiler to compile our code. Kind of these lines underneath them where I'm setting these variables, that'll be used in the next slide where I select the appropriate library in the merging step, where we're going to merge everything into one static library. So I know this slide is a bit of an eyesore to look at, but once again, please bear with me. As I mentioned earlier, if a developer wants to link against our library at this point, they will need to also link against all the dependency libraries in order to resolve the undefined symbol errors. So even though our app is pretty simple at this point, we already have 8 dependency libraries, believe it or not. The first is NCNN, then we have 3 OpenCV module libraries, then we have 4 other utility libraries, including libjpeg, libpng, zlib, and libtiff, which were all built as part of OpenCV. So we could require the user to build these dependencies themselves or ship them alongside our library, but ultimately that takes more work for the user, and we want to lower the barrier for use. The ideal situation is if we can ship the user a single library which contains our library along with all of the other third-party dependency libraries other than the standard system libraries, because we probably don't want to combine those into our own library. We can actually use CMake to achieve this, which is exactly what we're going to do. So we do this by adding a custom target shown here, and then execute what is called an MRI script. This MRI script, which is kind of like this whole section shown here, gets past the AR-M bash command, and this will basically combine all the static libraries into a single archive. What's pretty cool about this method is that it'll gracefully handle overlapping member names from the original archives, which sometimes tends to be an issue when combining static libraries. So you don't need to worry about that. So running this command will produce libmy_sdk.a, which will contain all of our archives. So let's hold up at this point and just give a quick recap on what we've done so far. We now have a static library called libmy_sdk.a, which contains our SDK library and also contains all the dependency libraries we require, which we have packaged into a single archive. We also have the ability to cross-compile and compile for x86 architecture as well, of course. So that's pretty great. Unit tests. So I probably don't need to explain why unit tests are important, but basically they are a critical part of SDK design that allows the developer to ensure the SDK is working as intended and that any later changes and refactors we make don't break things. And if they do, they help us identify what we've broken so that we can push out a fix as fast as possible. In this specific case, creating a unit test executable also gives us an opportunity to link against the combined library we just created to ensure it can link correctly and that everything's working as intended. So as mentioned earlier, we're using Catch2 as our unit testing framework. Basically how Catch2 works is that we have this macro called test case and another macro called section. So what's interesting is that for each section, the test case is actually executed from the start again. So in our example here, we only have one section written, just because that's all I could fit on the screen. But if we had a second section in our test case, then we would know that we are restarting with a fresh MySDK object, because it would basically, even if the second section is after the first section, it's basically restarting from the start and then going back to the second section. That's just how it works. We can then use macros such as require to check our assertions. So in this code here, what we're doing is that we're asserting that the number of faces detected in an image that I provided is equal to 6. I mean, we should really be checking other things to make sure the landmark detections are correct and that the bounding box locations are correct. But once again, this is all I could fit on the screen, so that's just what I'm showing for now. So I'll quickly show the CMake commands required to build our unit testing library. Basically, what I really want to emphasize here and point out is that we only need to link against our combined library, lib my_sdk.a, and nothing else. So all the dependencies have been put into this one library. So that's all we require. Okay. So we will be using Doxygen to produce documentation directly from our code. We can go ahead and document all the methods and data types in our public API using the Doxygen syntax shown below. So kind of this is how you can go ahead and document a struct, and then this is how you would go ahead and document a function. So with a function, it's a bit more involved. So you have a description, you kind of describe what the parameters are and say if they're in or out parameters, and then explain what the return value is. So that's how we write the documentation. Now we need to actually build the documentation. So in order to actually generate the documentation, we need something called a doxy file, which is basically the blueprint which tells Doxygen how to generate the documentation. We can generate a doxy file by running doxygen-g in our terminal. This is assuming you have Doxygen installed, which you can do using apt-get. We then need to go ahead and edit our doxy file. There's a bunch of like configuration you can do and things you can customize, but the bare minimum we need to do is to specify the output directory and also the input files. The input directory, which in our case, is only the public include header file. That's the only file which we want to have documentation. Finally, we're going to use CMake to actually build the documentation as a target. I won't be going over that because I'm sure you guys are sick of seeing CMake commands probably. And if you're interested, it's in the GitHub repository once again. So kind of once it's built, it'll look something like the image on the right. This is a generated HTML page. From here, you can use tools like Sphinx to further improve the documentation and make it more aesthetically pleasing. So the next thing we want to add to our SDK are language bindings to make it easier for developers to use, because let's be honest, sometimes C++ is not the easiest or fastest language to develop with. I'll be demonstrating this using Python bindings, but bindings for any other language are just as easy to write. So we're using the PyBind 11 framework for this, and we start by using the PyBind 11. We start by using the PyBind 11 module macro, which basically creates a function that will be called when an import statement is issued from within Python. So in our case, our Python module is going to be named MySDK. Next, we're able to define our class and their members using the PyBind 11 syntax. Now here's something to note. In C++, it's generally pretty common to pass variables using mutable reference, which allows for both read-write access. So that's exactly what we've done in our own member function. So if you guys remember, the second and third parameters in our getFacebox and landmarks function are passed by reference. One is a Boolean, one is a vector of faceboxes and landmarks. So in Python, all arguments are passed by reference. However, certain basic Python types are immutable, including Boolean. So since our C++ function takes a Boolean by reference and writes to it, we need to use the following workaround. We basically, within our kind of implementation, we need to define our Boolean, and then we pass it to our C++ function by reference. and then we return it as a tuple. So just for the sake of clarity, I've also done that with the vector as well. Okay, and now on to continuous integration. So for continuous integration for our continuous integration pipeline, we'll be using a tool called CircleCI, which I really like because it integrates directly with GitHub. Additionally, it will trigger a new build every time we push a commit automatically, which is pretty great. You don't need to do any more configuration there. So to get started, you go to CircleCI website and you connect it to your GitHub account, then you select the project you want to add, and that's really all you have to do. Once that's added in our project, we create a directory called .circleci, so it's kind of like a hidden directory, and we create that at the root of our project, and within that we create a file called config.yml. So for anyone who's not familiar, YAML, which is what the YML extension stands for, it's a serialization language commonly used for config files. So we can use it to instruct what operations we want CircleCI to perform. So in the YAML snippet I've shown, you can see how we're building for we are building one of our dependency libraries first, then later building the SDK itself. So it's probably advisable you run your unit test in your CI pipeline as well, which I've done, but I haven't shown in this file just because for the sake of space, it wouldn't fit on the screen. So kind of what's also cool is that if we're intelligent, we can use caching to significantly reduce our build times. So for example, in the YAML shown on the screen, you can see that we basically, when we build our OpenCV build, we'll actually cache the build based on the hash of the build script. And then on the subsequent build, we can basically see if the hash of the build script has changed, and if it hasn't, that means that nothing's been changed, and we can actually use our OpenCV library that we've previously built and that we previously cached, and that'll save us valuable time. Just another thing to be aware of, with CircleCI, we're actually running our build in a Docker image, so that's kind of like where we're building it in a Docker container, so that's kind of where our Docker directory was coming into play. I created a Docker image, which kind of installed all the Ubuntu dependencies we required, such as our Toolchains and Python and everything, and kind of we're building this inside that container. And there you have it. You survived the talk, and you've officially created a cross-platform SDK with language bindings, documentation, and set up a CI pipeline. And now I can open the floor to any questions. If you do have questions, please just